In this video, I'm going to be going over test number 2. So in the first question, it's asking which sequence of transformations shows that the two triangles are congruent. So basically, which sequence of transformations maps triangle EQA onto triangle SUL. So if we take a look at the first answer choice, it says rotate triangle EQA 90 degrees counterclockwise. And if we go 90 degrees counterclockwise, it'll land somewhere in this box looking like this, just a rough sketch of what it's going to look like, not exact, of course. And then translate 9 units to the right and 1 down. So that looks like it could work because it looks like we could go 9 units to the right and 1 down and we could land in the right place. Let's take a look at the other answer choices. And generally with these multiple choice questions, you don't actually have to do the transformations. Generally, there'll be like one obvious answer choice. So let's take a look and see if the rest of them we could knock out and, rule them out and be sure that it's answer choice number 1. So number 2 says rotate triangle EQA 90 degrees counterclockwise. So if I rotate 90 degrees counterclockwise about the origin, it'll be looking something like this, just like we had before. And then it says reflect over the line x equals 4. 1, 2, 3, 4. X equals 4 is right over here. So if we reflect over this line, it's going to land like over here to be equal distances from the line. So this answer choice cannot be it. So I'm going to rule out answer choice number 2. And let's hope we can easily rule out 3 and 4 just the same way. Otherwise, if we can't, we'll actually have to do the transformation. Reflect triangle EQA over the x-axis. So here's the x-axis. So if I reflect over the x-axis, it's going to look, and just a sketch. I didn't actually count the boxes, so it looks a little bit off, but just to see. And then rotate 90 degrees clockwise around the origin. If I rotate the reflected shape 90 degrees clockwise, it's going to land in this box. So I know that that is not correct because I need it to land in this box. So we can rule out answer choice number 3 as well. So this is going great so far. And finally, translate triangle EQA 10 units right, and then reflect over the line x equals -1. So let's see. 10 units right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And then reflect over the line x equals -1. Well, the line x equals -1 is over here. So if we reflect over that line, it's going to land over here to be equal distance. So it's going to jump over the line onto the side. So it's not going to go down here, which is where we need it to go. So answer choice number 1 is the only one that is reasonable here. So luckily, we don't actually have to try out the transformation. And a lot of times in those multiple choice questions, it will be like that. You should definitely go through all the answer choices, but generally there'll be one obvious answer choice. For question number 2, we talked a lot about parallelograms in class. We talked a lot about how parallelograms don't have reflection symmetry, but they only have rotation symmetry. So if you tried, sketching out the line y equals x or y equals -x, it might have appeared that they were lines of symmetry, but they're not, because remember, parallelograms don't have any lines of symmetry. So I can automatically just knock out 1 and 2. Parallelograms have no lines of symmetry. They do not have reflection symmetry. And that leaves me with just answer choices 3 and 4. And if I rotate 90 degrees, it's not going to look like itself. But if I rotate 180 degrees, it will look like itself. So that one, as long as you know that parallelograms don't have any lines of symmetry, don't have reflection symmetry, that one was an easy one to narrow down. Okay, so here we have a decagon, and in the parentheses, I did put that the decagon has 10 sides. They won't tell you that on the Regents exam. We need to find the value of n. That would be the degrees that would rotate the decagon onto itself. So we talked about in class that if we do 360 divided by the number of sides, we'll get the angle that you can rotate by to get the shape to look like itself. And of course, this only works when you have a regular polygon, which we have right now, and you're rotating around its center. So 36, but 36 is not an answer choice. So remember, every 36 degrees, it's going to happen. So 36, 72, any time you go 36 degrees, it'll happen 108, and you can keep going. So basically what I'm looking for is I'm looking for an answer choice that is a multiple of 36. So I'm going to take my calculator. I'll do 150 divided by 36. Now that does not work out evenly, so it's not answer choice number 2, and it can't be answer choice number 1. 225 divided by 36. Nope. Gives me a decimal. And then finally 252 divided by 36, and it works out to be a whole number. So 36 is a multiple of 252, so that will work. Okay, so over here, this is a question on the triangle inequality theorem. And the triangle inequality theorem says that if we add any two sides of a triangle together, it needs to be greater than the third side. So let's try out all the answer choices. So I'm going to make my triangle. 2 of the sides have length 2 and 8. And let's try out 10. If I add the 2 and the 10 sides together, I get 12. That is greater than the third side 8, so that's good to go. Let me add 2 of the other sides. How about 10 and 8? That's 18. That's greater than the remaining side 2, so that's good to go. The last 2 sides are 8 and 2. That's 10. 10 is not greater than 10. 10 is equal to 10. So answer choice 1 does not work. Goodbye to answer choice number 1. It does not satisfy the triangle inequality theorem. Let's try answer choice number 2. Same 2 sides of 2 and 8. And this time we're trying out 7. So 2 plus 7, that's 9. It's greater than the remaining side 8, so far so good. 7 plus 8, that's 15. That's greater than the remaining side 2, so far so good. And finally, 8 plus 2 equals to 10. Greater than the remaining side 7. So 7 is the correct answer choice. It satisfies the triangle inequality theorem. If you picked answer choice 3 or 4, then you should draw out like we did over here, and you should add 2 of the sides and just see that when you add 2 of the sides, it won't be greater than the third side. So you should definitely try drawing a picture and following what we did over here for answer choices 3 or 4 if you selected those. So in answer choice number 5, we know a reflection and a rotation happened. It tells us that in the question. So we know rigid transformations happened, so we know we have congruent figures. And when it says which statement is always true, it's basically just asking what matches up in the 2 triangles before and after the transformation. So you might be able to see that these triangles look like right triangles, right? We don't trust diagrams, but they look like right triangles. So like BC and EF look like hypotenuses, but the way to verify for sure is in the names of the triangles. So BC is the second and third letter. So it should map up to the second and third letter here, which is EF. So that statement is true. A doesn't match up to F. A would match up to D, actually. And those are both the angles that look like right angles, so you could have told from the diagram as well. AC is the first and third, so it should match up to DF, not DE. And then finally, angle B should match up to angle E, not angle D. So answer choice 1 is the one that matches up correctly. Here we have an exterior angle of the triangle. And remember that the exterior angle theorem for triangles says that the exterior angle is equal to the sum of the 2 non-adjacent interior angles. So 3x plus 10 plus x plus 40. I'm going to take a moment and just combine my like terms. We have 3x and x. That is 4x. We have 10 and we have 40. That is 50. I'm going to subtract 4x from both sides, and I have 2x is equal to 50. And then if I divide both sides by 2, I get x is equal to 25. Now be careful because 25 is an answer choice. It is the x value, but it's not what the question's asking for. Always double check and reread the question. It's asking for the measurement of angle CAB. So we do need to plug in. 25 plus 40 is 65 degrees. So the correct answer is answer choice number 4. For this one over here, the biggest mistake a lot of people said is just translation. So a lot of people said translate 1, 2, 3, 1, 2, 3, 4, 4 units to the right, and 1, 2, 3, 4, 5 units up. And that's not going to work, because if you translate 4 units to the right and 5 units up, yes, the shapes will match onto each other. But take a look at the letters. B is supposed to match up to G, but B's on the left of the shape and G's on the right. So when you slide it on, they're going to be in the wrong spots. Same thing with K and L. K is on the right here, but it should match up to L, which is on the left. So it's going to slide onto G. It's going to be in the wrong spot. So since the shape needs to flip over based on where the letters are located, the only way that we're going to be able to accomplish this is by using a reflection. So one way that people were doing it is they were reflecting over the y-axis. And I'll just take 1 point and show you. 1, 2, 1, 2. And then after you reflect over the y-axis, you can translate 1, 2, 3, 4, 5 units up. And K should match onto L, and notice now how K will go to where L is. So you can write that down, you can explain it, but we're reflecting over the y-axis and then translating 5 units up. You could translate first and then reflect, but this is the way that a lot of people were doing it. Okay, this one over here. So I'm going to take a moment and I'm just going to graph the quadrilateral. Okay, so first we're reflecting over the line x equals 1. A lot of people messed up with this. I saw a lot of reflecting over y equals 1, x equals -1, the y-axis, the x-axis, a lot of other lines. So the line that we need to reflect over according to the question is x equals 1, which is the vertical line through the x coordinate of 1. So this is the line x equals 1. So I'm going to first reflect over the line x equals 1 by just counting the spaces to my line and then moving an equal number of spaces over the line. And there we have it after reflection over the line x equals 1. And now we need to do a rotation. We're going to rotate 90 degrees counterclockwise, centered at the origin. So the origin, which I'm dotting in red, is going to be our center of rotation. So when I rotate it 90 degrees counterclockwise is going to be that way. So it's going to put it up into the box on top. And remember, it's going to turn. So I like to visualize the general shape it's going to have. I'm going to actually plot that out in a second, but when it turns, it's going to have a shape like this. So it's always good to visualize what it's going to look like. So that way you have an idea, okay, it's going into the box it needs to go into, it turned the way it's supposed to, and then you can just figure out if the distances are correct. Remember, when we do rotation, the pre-image points and the image points have to be the same distance from the center. So right now T is 1, 2, 3, 4 to the right and 1 down from the center. So I want to make sure that when I rotate it, it's the same distance. And where I put it over here, 1, 2, 3, 4, 1. So it uses the same numbers 4 and 1. So that's really important to make sure that the distances are the same. And the way I figured out, where it's supposed to go is also by trying to visualize how it was going to turn. So remember, it's important to keep in mind how it's going to turn so you can figure out generally where the point's going to land. And then you can also count and just make sure that it uses the same numbers from the center. If I'm going from the center to the pre-image point, 4 to the right and 1 down, I should use those same numbers, 4 and 1, to get to the image point. Okay, I'm going to do one more point and then I think we should be good. Well, actually, I don't even have to do H prime because now that I apply the T prime, I can just count. There's 2 spaces in between. So I'm just going to go 2 spaces over here, and that's going to be H double prime. And I'll just verify the distances. So from the center, 1, 2, 3, 4, 5, 6, and 1 down. 1, 2, 3, 4, 5, 6, and 1 over. So it uses the same numbers of 6 and 1. So far, so good. So I think if I could just do one more point, it'll be fine. So I'm going to do point A. So from the center of the point A, 1, 2, 3 down. 1, 2, 3 over. So I want to use 3 and 3. So let's do it. 1, 2, 3. 1, 2, 3. And once I have A double prime, it's the distance between A and M is 1, 2, 3, 4, 5 spaces. So I could just dot where M double prime should be. There we have it, the rotated quadrilateral. So just make sure that you count the spaces from the center and just make sure the distances are the same. So yes, rigid transformations, and a really good word to use is rigid transformations, especially on the Regents exam. Keep side lengths and angle measures the same, creating congruent figures. So for this one over here, it says explain, so you do need to explain in words. So even if you have all the right angles marked in the diagram, you actually will not receive credit for this question on the Regents exam unless you have your explanation in words. So I'm going to go through how that explanation should look now. First, let's talk about the angles that we need. So we're told in the givens that these two lines are parallel. Angle EFG, this angle right over here, is 32 degrees. And angle AEG is 137 degrees. We need to figure out what the measure of angle EGF is, so this angle right here. So I need to get closer to it. What I'm going to use, and you could use alternate interior angles. We do have parallel lines. That relationship definitely exists, but I think the most direct way is to recognize that these two angles form a linear pair. So 180 minus 137 is 43. And then we know that all three angles of a triangle add to 180. So if I do 43 plus the 32, I get 75. And then if I subtract that from 180, I get 105 degrees here. So even though this is right, this would not get credit because you do have to explain in words. So I'm going to put that over here. Since angle AEG and angle FEG form a linear pair, angle FEG is 43 degrees, since 180 minus 137 equals to 43 degrees. Since all three angles of a triangle sum to 180 degrees, I added the 43-degree angle and the 32-degree angle in triangle EGF and got 75 degrees. The missing angle is 180 degrees minus 75 degrees, which is 105 degrees. So you do need to explain in words. Doesn't need to be a whole book, but the angles that you're using need to be explained. So I just used the fact that we had a linear pair and then that all the angles of a triangle sum to 180. If you did use the parallel lines and like the alternate interior angles, then you would mention that, but you didn't even need to use it here. Wasn't necessary. Okay, let's take a look over here. So you got 1 point for marking your diagram, and a lot of people miss this point. You just need to mark the givens. So BC is parallel to AD, and AB is parallel to CD. If you are correcting your test, you should redraw your diagram on a separate piece of paper and put the correct markings in. And that's why a lot of people were having trouble seeing what was going on in this proof, because the diagram wasn't marked. Because if you take a look at your proof statement, you're trying to prove that angle BCD, which is this angle over here, is congruent to angle BAD, which is this whole angle over here. So you're trying to prove the big angles. And if you take a look at the proof, since it was a fill in the blank proof, it gives you as one of the reasons that you're using addition. So it kind of directs you, okay, that in order to get from 4 to 5, so in order to get to the end, to the angles that we want, that we're looking for, we're going to need to add things together. So then what I do is I ask myself, okay, well, what are the pieces of those two big green angles that I need to add together? So if I add these two pieces together, then I get the whole green angle BAD. And if I add these two pieces together, I get the whole green angle BCD. So now I just need to figure out how I'm going to get congruent pieces for my addition to work. Because remember, for addition, we have to start with congruent, we have to add congruent, and then we get congruent. And that's where marking the diagram comes in. If I highlight these two parallel lines and the transversal that connects them, you'll see the letter Z. So in the corner of the Z are alternate interior angles, and they are congruent because we have parallel lines. So this and this are in the corner of that yellow Z. They are alternate interior angles. We also have these two parallel lines. And if I highlight the transversal that connects them, you'll see another letter Z. It's just sideways, but it's a letter Z. And in the corner of the Z, we have congruent alternate interior angles because the lines are parallel. So now we know the pieces are congruent. They're alternate interior angles that are congruent when lines are parallel. So now we can add those pieces together to make the whole thing. And that's really the whole proof. That's it. So let's work backwards. After addition or subtraction, our reason is always substitution. And the reason for that is we're always saying what the things we added or subtracted leave us over with. So now let me figure out what we added. To make angle BCD, because that one's written first, we need BCA and DCA. To make angle BAD, we need DAC and BAC. And now you can see what I was saying about the substitution, that BCA plus DCA make BCD, and that DAC plus BAC make BAD. So we're just saying what our addition leaves us over with. We're saying this plus this is this, so we can replace it with this. And that's the substitution that always follows the addition or subtraction to tell us what we're left over with. So that's the hard part. the addition. So now it's just stating why the angles are congruent, because remember, we have to start with congruent and we have to add congruent. So we need to know that the two purple angles that we're adding are congruent. And we need to know that the two brown angles that we're adding are congruent. And we already talked about how they're both two pairs of alternate interior angles. Since they use the same reason, you can write it out twice, but I'm just going to write it big. Alternate interior angles are congruent when parallel lines are cut by a transversal. You can't just write alternate interior angles. The Regents exam will not give you credit for it. You can't just write alternate interior angles are congruent, because they're not always congruent. The Regents exam won't give you credit for it. You have to mention that they're congruent because of parallel lines, because alternate interior angles are only congruent when we have parallel lines. Otherwise, you do not know that they're congruent to each other. And that's our whole proof. Also, another thing about addition or subtraction, if your result is angles, like our result was going to be here, if we're using addition to get angles, then you should be adding two smaller angles together. You can't add segments to get angles, right? That doesn't make any sense. So please be mindful of that. If you're trying to get angles through addition, you should be adding smaller angles together. Here's the extra credit, which is not really too difficult based on what we've learned in class. So notice we have an isosceles triangle from the givens. We have AB congruent to BC. And we spoke about how when a triangle has two equal sides, the angles opposite from those sides are congruent. It was the base angle theorem. The base angles of an isosceles triangle are congruent. So then we have another given. So that was a conclusion that I drew from the first given. The first given was that AB is congruent to BC. And then we have a second given that BC bisects angle ACD. So angle ACD is being split into two equal parts. So that's 1/2 and that's 1/2. And now I can see that all three angles I have here should be congruent to each other, because if angle A is congruent to angle BCA, and angle BCA is also congruent to angle DCB, then all of these should be congruent to each other. And that's the whole proof here as well. So let me just change the markings since we've established that they're all congruent, and then I'll write up the proof. I'm just going to write an S and an R. So I'm going to state that the base angles are congruent, angle A and angle BCA. You should not write base angle theorem. You should not write, I don't know what else, but you should write out what you're saying. If two sides of a triangle are congruent, the angles opposite are congruent. And now I'm going to say that angle BCA is congruent to angle DCB. And that was due to angle DCA being bisected. And an angle bisector splits an angle into congruent parts. And then finally, since angle BCA is congruent to DCB, and angle BCA is also congruent to angle A and angle DCB have to be congruent to each other. If two things are congruent to the same third thing, then they must be congruent to each other. And that is the transitive property. And that's the whole proof. I hope you see that marking the diagram is really helpful.